Okay folks, here we go with everything you need to know about projectile motion. Most important thing to know about projectile motion is we can split the motion of a projectile into a horizontal component and a vertical component. And the obvious question is, why would we do this? And the answer is, it's easier and usually quicker to do two simple calculations than one longer, more complicated calculation. So essentially, the horizontal component will be cos theta times whatever it is you're interested in. The vertical component will be sine theta times whatever you're interested in, and that comes from, if that is the initial launch of the projectile, so it's got some velocity v at an angle theta above the horizontal, then we can make a nice little triangle, and hopefully you can see that v vertical must be v sine theta and v horizontal must be v cos theta, as we've talked about before. What we'll do now is talk about the first of two classic examples of projectile motion, the horizontal projection. This is when we have some object which is travelling horizontally, which then suddenly starts to travel like a projectile. Now this could be something like something being rolled off the top of a table. It could be something being thrown horizontally off the top of a building. And there's even a fairly famous past paper question where an osprey is flying horizontally, carrying a fish that it's just caught, and then for some reason loses its grip on the fish. Now, if you've ever seen an osprey in real life, the claws on those things are kind of, like the size of my finger. It's not dropping anything by accident, so that's not at all a realistic example. But we can make it an example for a question. So what am I writing in here? I'm writing in SH for the horizontal displacement. I've already got SV for the vertical displacement. I'd have UH for the initial horizontal velocity. And how do I deal with this problem? Well, I deal with it by making a little table. Horizontal, vertical, final velocity, initial velocity, acceleration, time, displacement. Now, if we take, let's just say it's that osprey, and it's flying horizontally, it drops the fish there, and the fish proceeds to arc downwards and then splash into the water there. What do we already know? Well, we already know that because the fish was being carried by the osprey and the osprey was flying horizontally, the initial vertical velocity is 0. We know that gravity is 9.8 meters per second squared because we're supposed to remember that. We know that, at least for the purposes of higher physics, there is no horizontal acceleration unless we get told that there is. That means that the initial horizontal velocity and the final horizontal velocity are going to be the same value. And what else else do we know? We know that since the fish doesn't magically split in two and take different amounts of time to travel horizontally and vertically, that's the same fish, it takes the same amount of time, so that means that whatever the vertical time and the horizontal time is, they are the same time. Like so, I'll put H for horizontal. It could put V for vertical. In fact, let's put TV equals TV. And then what would we need to do? Then we would need to work out a specific solution based on a specific example. So let us say, for the sake of argument, that in this example, the osprey was flying at, let's make it 12 meters per second, before it drops the fish, flying horizontally at 12 meters per second. And let's say that it takes a time of, let's say 3 seconds for the fish to hit the ground, the water rather. What can we work out? Well, we know 3 values and we can deduce that things are equal to other things. And there are 3 that at present we don't have any idea about, but we can work them out fairly easily. So for example, we can work out the horizontal displacement, SH equals UH TH plus a half AH TH squared. So if we're saying that TH is 3 seconds, UH is 12, then the horizontal displacement is 12 times 3 plus a half times 0 times 3 squared. So that's going to give us 36 meters. This bit's going to be 0. So we know that. Excellent, good. Do we know the final horizontal velocity? Yes, we do, because it's equal to the initial horizontal velocity. So we know this one, this one, and this one, and this one. Oh, and because that equals that, we know that one. That means we've only got 2 things left to work out. That was easy. Right then, what can we do? Let's go for the final vertical velocity equals the initial vertical velocity plus the vertical acceleration times the vertical time. So the final vertical velocity will be the initial vertical velocity, which was 0, plus the acceleration, 9.8, times the time. Well, we said it was going to be 3 seconds for the purposes of this example, so the final vertical velocity is 29.4 meters per second. Imagine a big salmon hitting you on the head at 29.4 meters per second. That would hurt quite a lot. Quite a lot of kinetic energy in that. So it'll make a big splash when it hits the ground. Okay, so we know that one, and that just leaves us with the vertical displacement. In other words, how high was the osprey flying when it dropped the fish, in the way that ospreys don't drop fishes. So vertical displacement equals initial vertical velocity times the vertical time plus half of the vertical acceleration times the vertical time squared. Let's see, well, the initial vertical velocity was 0, so this bit's going to be 0. I'll write it in properly just to show completeness. A half times 9.8 times 3 squared. So that's going to be 0, and that's going to be 9 times a half is 4.5. 4.5 times 9.8. Ooh, what's that? That's 4 9s are 36. 4 8s are 3.2, so that'll be 39.2, and then the halves are 4.9, so that'll be 43 point something. Nope, it'll be 44.1 meters. There we go. Now, the other classic example of projectile motion is when the projectile travels in a parabola. Okay, so we'd have, starting there, projectile goes whee in a symmetric parabolic arc. Now, obviously in the real world, air resistance means it wouldn't be exactly symmetrical, but in physics exam land, at least for the purposes of hire, we're going to ignore that air resistance and it's going to be symmetrical. So there is whatever level it's taking off on, which we'll call point A. We'll call the highest point on the arc point B, and we'll call where it lands point C. So between point B and the level will be the vertical displacement, between point A and point C will be the horizontal displacement, and there'll be a horizontal time that will go along with that, and there'll be a vertical time that will go along with that. And because it's symmetrical, we can deduce that the vertical time must be half of the horizontal time. And that's going to come in very useful when we try to solve these things. So again, we make our little table, vert for vertical, not for green, haha, French joke there, and horiz for horizontal, V-U-A-T-S. Okay, let's fill in what we already know. Horizontal acceleration, 0. Vertical acceleration, negative 9.8 meters per second squared. Now, at this point, hopefully most of you are going to go, hang on, in the previous example it was 9.8. Why is it now minus 9.8? And that is because of the direction that the projectile starts moving in. In the previous example, the projectile started moving horizontally, and then we introduced a vertical component downwards, which is in the same direction as gravity, so plus 9.8. In this example, there is a horizontal component and a vertical component, but the vertical component here is pointed upwards. So that's the opposite direction to gravity, so we're going to make it minus 9.8. If you don't believe that as an explanation, just trust me, it works. What have we got? Well, we've got horizontal and vertical components of the initial velocity, vertical and horizontal components of the final velocity. We've got times, we've got displacements. We're going to need to actually start giving some numbers for an example here. So what we're going to do is Mr. McCann's famous goalie goal from when he was playing ice hockey. And it was one of those weird situations. The other team had pulled their goalie to try and get an extra attacker on the ice. And I got the puck here, just in my goal crease, and flipped it as far away from my goal as I could possibly get, because we're quite near the end of the game. We're 1-up, and we're about to win. And what happens is the puck goes whee through the air, bounces in the opposition's goal crease, and slides into their net, because of course their goalie wasn't there because they put an extra attacker on. Total fluke of a goal, but I'm claiming it as fame anyway. So that means that SH was about 60 metres, because that's 200 feet from goal to goal in an ice hockey, an NHL-sized ice hockey arena. So that's about 60 metres. And I'm going to say, it took about 2 seconds, I think, to get from there to there. Can we work out everything else? Well, for a start, I better put the 2 seconds in the right place, hadn't I? So that go there. Have I put it in the right place? If it took 2 seconds to get from there to there, is it 2 seconds vertical? No, it's not. It's 1 second vertical, because the vertical time is half of the horizontal time, because it's a symmetric parabola. Right, now with all that straightened out, and these numbers in the right place, let's see what we can work out. Can we work out the horizontal velocity? Well, we've got a displacement and a time, so we should be able to. Let's go for it. SH equals UH plus, not plus, times TH plus a half AH TH squared. SH equals UH is what we're trying to find out. SH is about 60 metres. TH is about 2 seconds plus a half times 0, because there's no horizontal acceleration, times 2 squared, so that's going to simplify to 60 equals 2UH, which means UH must be 30 metres per second. And because there's no horizontal acceleration, this also equals VH. So that's those two worked out. And we don't have any more horizontal things to work out. Excellent. Right, let's see what we can do. Vertical displacement, initial vertical velocity, final vertical velocity. Let's see. What can we do there? Well, if we make the final vertical velocity at point B, then the vertical velocity at point B is 0 meters per second. And that's going to allow us to unlock the rest of the problem for the vertical parts, because we can do then VV equals a UV, a plus AV TV. And if we're going to say that's 0 at that point, which it is, so 0 vertical velocity at the highest point in the parabola, UV plus negative 9.8 times the vertical time, which is 1 second because it's symmetric, so the vertical time is half of the horizontal time. So that's 1 and not 2. So 0 equals UV plus negative 9.8 times 1. So you use your maths genius skills to go UV is 9.8 meters per second. So that's that and that done. And then the only thing we've got left to do is the vertical velocity. Well, before we get to working that out, I reckoned after the match that it was about an angle of 30 degrees and it was a maximum height of about 5 meters. In other words, I reckoned the puck left my stick at about 30 degrees above the horizontal and it got to a height of about 5 meters as it flew through the air and then eventually arced back downwards into the other goal. Let's see how accurate I was in those guesstimates based just on observing what happened. So, vertical displacement, UV TV plus a half AV TV squared. Okay, SV. UV, we worked out just there, was 9.8. And we worked out that vertical time was 1 second because it was half of the horizontal time, which was 2 seconds. It was 1 plus a half times negative 9.8 times the 1 second squared. So 9.8 times 1 is the 9.8. 1 squared is 1 times a half is a half, times negative 9.8 is negative 4.9. So SV, 4.9 meters. Looks like I wasn't too bad at estimating the height. Now, for how good was I at guesstimating the angle, we can use the initial vertical velocity and the initial horizontal velocity to make a triangle. And once we've made a triangle, we can work out the angle. So UV we worked out was 9.8 meters per second. And UH we worked out was 30 meters per second. So what angle did we get and how are we going to work it out? Well, if you've been paying attention in maths, you're going to go tan theta equals opposite over adjacent. So that will be 9.8 over 30. And from that, you're going to work out that the angle is 18.1 degrees. So it seems that I'm reasonably accurate at estimating heights, but not very good at estimating angles. So I'm going to put a big question mark here next to my 30 degrees.